Alright, in this section we're going to look at infinite limits. And in fact, with infinite limits, we're going to look at vertical asymptotes. So first of all, we want to look at the limit as x approaches 1 from the left, as x approaches 1 from the right, and then we're going to look at a different graph, the limit as x approaches 1 of 1 over x minus 1 squared. I have these graphs already up on a graphing calculator here. This graph right here, this graph is 1 over x minus 1, and in our notes we wanted to look at what happens as we approach 1 from both the right and the left. So as we approach 1 from the left, so we're coming from the left, as we approach 1, if we plug in values or look in this graph, we notice if we keep going down, this graph is going to continue and continue and continue, but it's never, ever, our x value is never, ever going to equal 1. So we would say the limit as x approaches 1 from the left is the y values approach negative infinity. They'll never stop. They approach negative infinity. All right, so let's take a look as it goes to the right. Take a look as a limit as x approaches 1 from the right. Looks like it keeps going on. It's never, our x values are never going to equal 1. And the y values are going to continue to get bigger and bigger, so the y values are going to approach positive infinity. So the limit as x approaches 1 from the left side was negative infinity. As limit approaches 1 from the right side is positive infinity. If we were to ask just simply what the limit as x approach 1 of this function, we would say it doesn't exist because they don't approach the same thing. In fact, when we say that x approaches negative, when x approaches 1 from the left, we said it approached negative infinity. Don't let this equal sign screw you up. This equal sign doesn't mean that the limit equals infinity. Infinity, we don't really know what it is. It's a huge thing. We don't even know what it is. It's just saying that that's what our limit approaches. It approaches, it just keeps getting bigger and bigger. In fact, that limit does not exist. It's just saying that that's what it approaches. So don't let that equal sign screw you up. It just means that the limit approaches infinity. We don't have an actual limit. Now let's look at the graph of 1 over x minus 1 squared. And we wanted to look at the limit as x approaches 1 from both the right and the left. Well, just the limit as x approaches 1. Well, we know that if the limit approaches the same thing from the left as it does from the right, the limit exists. So if we look as this function approaches 1 from the right, it approaches and the y values get bigger and bigger and bigger. So it approaches positive infinity. As we go follow this graph from the left, again, it's going to approach positive infinity as x approaches 1. So we would say the limit as x approaches 1 of 1 over x minus 1 squared, since it approaches the same thing from both sides, we say the limit is infinity. Again, that's not to say that the limit exists. It's just telling us what it approaches. All right. Moving on. Vertical asymptotes. If f of x approaches infinity, just like in our cases up above, or negative infinity as x approaches some value c from the right or the left, then the line x equal to c is a vertical asymptote on the graph. So on our graphs above, we had a vertical asymptote at x equal to 1. In fact, if you remember from pre-calculus, it was whatever made our denominator equal 0. That would be whatever make the function undefined. Let's go further into what vertical asymptotes mean. All right, let f and g be continuous on an open interval containing c, so some value c. If f of c, we plug it in, does not equal 0, and g of c equals 0, then there exists an open interval containing c such that, so basically what it's saying is we have a vertical asymptote. So what it says is both of these can't equal 0. We can't have 0 over 0. But as long as f of c, so we plug some number in f of x and we say we get 5. And we plug some number in g of x and we get 0. We know that there is a vertical asymptote at whatever number we pick to plug in. All right, just as long as we don't have 0 over 0. Oh, in example 1 here, determine all vertical asymptotes of the graph of each function. Well, we look to start off what values are going to make our denominator equal 0. So we'd say, when does x squared minus 1 equal 0? Add our x over x squared equals 1. x equals plus or minus 1. We take the square root of both sides. So in fact, we're going to have a vertical asymptote at plus or minus 1. Now I know that because if I plug plus or minus 1 in here, it's not going to make the numerator 0 either. It'll make the denominator 0, but the numerator will be some number. So it's got to be some number over 0. When I plug 1 in, 1 squared is 1, I get 2 over 0. When I plug negative 1 in, I get 1 plus 1 is 2 over 0. So at x equal to plus 1 and x equal to minus 1, we have a vertical asymptote. Remember, the numerator cannot equal 0. A nice little note for you right here. Example 2. Determine all vertical asymptotes of the graph. Well, again, we start by looking at our denominator. When does x squared minus 4 equal 0? Well, x squared minus, well, add our 4 over x squared equals 4. X equals plus or minus 2. Well, let's check a little farther. We got to make sure that the top doesn't also equal 0 for these values. So plug positive 2 in. If I plug a positive 2, I get 4 plus 4 minus 8. Uh-oh. Positive 2 is not going to be an asymptote because we have 0 over 0. All right, so positive 2, throw that one out. Try negative 2. So I'm going to get 4 minus 8. So I get a negative 8 over 0. So at negative 2, so at x equal to negative 2, we're going to have a vertical asymptote. However, you should remember from pre-calculus that at x equal to 2, we're probably going to have a hole. If we were to factor this, all right, two numbers that multiply to be 8 add up to be 2. We're going to have a plus 4 minus 2, x minus 2. And on the bottom, we know that this bottom is the difference of perfect squares, so it would be x plus 2, x minus 2. Well, these x minus 2's cancel out, or we say in quotations cancel out. They actually, is what we were doing in limits. The graph of this function is going to look like this graph right here. Is going to behave like that graph for every value except for x equal to 2, because in this equation right here, x equal to 2, it can't happen. All right, cancel out. In fact, we have a hole. If you remember from pre-calculus, we have a hole there. All right. So just a quick reminder from pre-calculus, and maybe if you forgot, hopefully taught you a little something new. Here's the properties from page 83 for us. Just some properties of limits. I'm saying the limit of f of x equals infinity. The limit of g of x equals some number. 5, whatever. All right. So we're saying some properties of limits are saying, so if we add, so this limit, remember when we added or subtracted limits, it'd be the limit of f of x plus or minus whatever we're doing, the limit of g of x. Well, if the limit of g of x or f of x was infinity, we have infinity plus or minus some number we called 5. Well, 5 plus infinity, we don't know what that is. It's either infinity plus 5 more or infinity minus 5. We don't know what that is, so it's basically infinity. That's why that is. That's why that one's the case there. The product rule again. We said we could multiply the limit of f of x, and we could multiply that times the limit of g of x and have our limit. Well, when I take infinity times some number, which we're calling it L, say it's 5, so 5 times infinity is going to be infinity. Now this little clarifier right here, if L is bigger than 0, so I pick 5, so it's going to be a positive infinity. If L is less than 0, so I picked a negative number, so I have infinity times a negative number. Anything times a negative number is going to be a negative, so that's why I would approach negative infinity. And the last rule here, the limit as x approaches some number of g of x over f of x. So I have some number, we've been saying 5 all over infinity. Well, if we think about how fractions work, all right, 1/2 is a bigger fraction as 1/4, and 1/4 is bigger than 1/8, and 1/8 is bigger than 1 over 100. As these bottom numbers get bigger and bigger and bigger here, our fraction gets closer and closer and closer to 0. So as we approach infinity, so we have the biggest number you can possibly think of in the denominator, we're going to have a really close number to 0. So that's why the limit as x approaches c of some number over infinity is going to equal 0.